Yeah, exactly. Because before I start, maybe I'll give you a little bit of an introduction to Adicsys. And Adicsys is a company that's based in France. In France, we have cheese, wine, a sense of humor, and quite a bit of momentum in FPGA design, and which is something that is not widely known because it doesn't go into commercial FPGAs. But if you look right and left on this aisle, there are FPGA-based verification systems that are designed in Paris. Did you know that? So, the team at Adicsys has been working on embedded FPGA projects for 10 years. Actually, it's closer to 15. And what we've been doing is something that gave us quite a bit of insight into embedded FPGA integration in ASICs. What this means is that we kind of know what we talk about, but mainly we run into many of the challenges that our designers are facing when they try to integrate an FPGA in an ASIC. And so in 2010, we took this experience and this know-how into an independent IP company. We spent 2 years developing the software and started doing business in 2012. And we started doing that with a kind of FPGA block that we would have liked in our prior lives. Because our prior lives integrating embedded FPGAs, they were not easy. There was a lot of tears, a lot of sweat. So before I come to the core aspects of what we think is important for an embedded FPGA to be successful, we can look at the very high-level use case for embedded FPGAs. And these use cases, they are broken down into two categories. They are not continuous. You'll see that it stops at 10% and starts at 50 again, but this is just an illustration. They are the ASICs where the embedded FPGA, whether it's one FPGA or a bunch of small FPGAs that are scattered all over, the embedded FPGA is not going to take more than as little as 1% of the total chip area. So this is what is kind of illustrated here. Really teeny tiny FPGAs. And those FPGAs, they can be used to customize I/O interfaces. That's the case where we see the smallest possible FPGAs, a couple of hundred lots, where you can basically customize a shift register or customize an interface. And that's interesting when you don't know up front where your chip is going to sit, potentially in a prototype, where you didn't have all the specs for your prototype or the specs for the board. Tiny FPGAs are also interesting to implement adaptive algorithms in different areas, and crypto applications are really interested in what we do. Of course, anything that is RTL-based, as long as it fits, will also apply to this first category of smaller embedded FPGAs. And then there's a second category. And 50% is just an illustration. It could be 30, it could be 80%. But in that case, the embedded FPGA is taking up most of the chip area. In that case, you would probably don't want to call this an ASIC anymore, or SoC. You would want to call it a custom FPGA. So basically what you're doing, you're building an FPGA that has features that you cannot buy off the vendors, like Xilinx or Altera. And this is what our friends from Mentor do. So, assuming that we are now, a chip architect, we have identified the embedded FPGA feature to be something that is of benefit for the final product. What's interesting to understand the process of integration is to look at the decision process that has to be gone through in order to make sure that it's the right solution, that is going to work fine, and that it is going to be acceptable by the design and engineers. So obviously everything that is on the side of RTL programmability, it's what comes with FPGA. So I'm not going to go into the details of that. This is why someone goes embedded FPGA. It's because they want RTL programmability for whatever reason. Then there's one downside, and in our IP, there's nothing hidden. Everything's visible, and I'll come to that later. But area is a downside of FPGA. Whether it's FPGA or embedded FPGA, and this is what is kind of illustrated by this picture here. This black box shows an ASIC gate, and in an ASIC gate you have a fixed gate that has a logic function, and they're connected with metal wires that run on top of the ASIC gates, and they're pretty much free because they're in the metal stack of the technology, and so it's free. If you want to do the same thing with an FPGA, then your fixed ASIC gate has to be a generic gate that has to be able to map all kinds of function. So that's bigger already. But then the metal interconnects, they also need circuits, muxes, transistors, whatever. This is also taking more space. And finally, you want all this to be programmable. So you need some kind of configuration space. Put all this together, it's bigger. What this means is that ASIC is not dead, but that also means that you cannot replace everything with our solution. It would be great, but it's just not possible. So understanding this is what will get you into the right category. This 1 to 10% ASIC area, or the 50%, the bigger custom FPGA project. Then finally, there's the less obvious questions, but these are the real important questions that I want to answer here. When you choose an embedded FPGA, you want to ask yourselves if the embedded FPGA architecture is ready to use. You would expect that from any vendor. When you buy a chip from Xilinx, it's ready to use. You want the same thing for an embedded FPGA. You don't want to be forced into going into architecture exploration. And the second question, which is probably the most important, is my ASIC flow unchanged when I embed an FPGA? So it's something that's really specific to FPGAs because FPGAs, they come mostly from the custom layered world. So they come as hard blocks. Hard blocks are more difficult to integrate in a chip, and they would answer no. In our experience, we've done both. And in order to make embedded FPGAs a possibility for everyone, we've tried very hard to answer yes to these two questions. So to explain why the second question is the most important and what is possible is to compare standalone FPGAs with embedded FPGAs. For an embedded FPGA, a customer could go any process node. So we've gone as high as 130 nanometers, which we were surprised, but it's because it's an old technology. And of course, all the latest nodes. Every customer might have a different request in terms of gate complexity. Some customers want really small, does it work? Really small equivalent FPGAs, some want big FPGAs. If you add to that the realization that an embedded FPGA can be customized for you, if you multiply all these possibilities, you come up with the conclusion that there's virtually an infinity of possibilities for an embedded FPGA block, which is very different from a standalone FPGA where your preferred vendor has already made choices. And now, the main difference, of course, is that your embedded FPGA is on your silicon. So who has ever worried about how big or how a vendor's FPGA was tested? No one. You buy them, you use them. But an embedded FPGA, it's sitting right on your silicon. So at some point, we're at DAC. We all understand what verification means. We all understand what a tape-out means, what the money behind that is. This means that at some point, your embedded FPGA has to verify just like the rest of your ASIC. And this is what is key. This is our experience. This is what we pulled out of this, these 10 years where we're doing all the kinds of projects. And so if you look at how the integration process of an embedded FPGA should look like, it can be simplified like this. So you want you will have a choosing process where a chip architect or marketing person or even a designer decides what kind of embedded FPGA will be best fitting his needs depending on the particular application. And once this is done, this is something that we help our customers with, because this is where it's important to make the right decisions, and especially this is where it's important not to choose too big of an embedded FPGA. Once this is done, this black arrow here, it symbolizes the handover to the technical people, to the designers. And what's important here is that you don't want your designers to become experts in FPGA design. Well, not in FPGA architecture, at least. So what's important is that your IP here, you need to be able to take off the fact that it's in the FPGA. Basically, once it is sitting on your top RTL project, it has to be handled just like anything else in the process, and it has to go through all the standard EDA tools that have already been chosen for you by your CAD group, by your foundry, or by yourselves. So for instance, in this integration process, what the design engineer will want to do is an RTL simulation of a bitstream loading. So this is something that never happens with a standalone FPGA. So it's something that our customers discover, and it's something that they have never done before. What this means is that in simulation, you make sure that the compiled bitstream can be loaded into your FPGA, and then your FPGA starts an application that properly behaves and communicates with the rest of the chip. This is as important as doing a reset simulation at the gate level. If you don't do that, you might have integrated the IP the wrong way. And this is an embedded FPGA in an ASIC, so you're not going to be able to patch a board or unsolder the FPGA that you bought standalone. So to summarize all this, we came up with this picture, and this is probably the picture that you want to remember about us. In all this, sorry, what's really important is that the FPGA block, the square that you will see on your floor plan, or the feature that you will see in your final data sheet, is really only the tip of the iceberg, and the whole IP solution that we provide and that we have built so that it can be integrated by anyone. Most of what you don't see, and hopefully you will never have to see it, is the preparation work at the FPGA architecture level, because it's not quite exactly the same type of FPGA than the others. It's adapted so that it's testable, and it can be handled by standard physical design tools, synthesis tools, timing analysis tools. But this is the picture that you might want to remember. The FPGA IP, it's not just a piece of circuitry, it's a whole solution. And this is what we provide. And so, just to rub it in a little bit, what we have focused on is to make sure that the people that we sell our IPs to, especially the designers, they don't have to go through a training to understand how an FPGA works and how the software works. It can be used just as a standalone FPGA right out of the box at the ASIC design level, at the verification level, and later when your product is out by the end user. And what's important is that we've made sure that we do not create a design gap, that we do not insert any type of black box, nothing that cannot be checked or rechecked by your design engineers with the great tools that you'll find here, no matter which tool. And this doesn't mean that you have to verify our IP, because our IP is out, it's on silicon, they're happy people with it. But you're building an ASIC, so you want to have the tools that will allow you to check something if you want to. And a good way to assess this is to realize that the RTL IP, which is the embedded FPGA model that you simulate at the RTL level, it's the source of the hardware that you finally synthesize and place on your silicon. So what you simulate is what you instantiate. There is no model for this. It's the actual IP that is transformed into silicon. And there's a picture here of a small embedded FPGA that has been placed and routed with a cadence tool. What's also important, we provide BIST because existing ATPG vector generation tools, they cannot handle FPGAs, not yet anyway. So we provide this BIST tool, and what is cool is that it can be run in the field as a self-test, as a bonus. And finally, I haven't said much about the embedded software. At some point, your FPGA, your embedded FPGA, is going to be a real product and real silicon. So everything that was important for the designer and the engineer at the ASIC level will have to apply to the embedded software.